Okay, we'll start out with a problem from as an Atwood machine, which is a machine of the different masses connected at ends of a string going around a pulley, and the one with the larger mass will accelerate downward, and it will accelerate more depending on the difference in depending on how different the masses are. The more different the masses, the more acceleration, with the maximum acceleration going to g of 10. So, so this is just an example problem where we have one mass around to a smaller mass. So in this problem, which I'll write out here, an Atwood machine is made with a 20 kilogram block. On one side and a 2 kilogram block on the other side. What would the acceleration of the blocks be? And what will the tension in the string be? Okay, so for a problem like this, you draw two free body diagrams and make use of the second law. And so let's make this sort of the blue mass. We'll make that 20 kilograms. And this one over here is our 2 kilogram mass. Now they have the same acceleration, okay, because it's the same string. But in the 20 kilogram, the Fg, the weight of that, is beating out the tension. So the Fg is the winner. And in the other one, the same Ft, but in this time, it's beating Fg, going down. So if we set up these two sum of the forces on here, we could do the blue side. The sum of the forces is mass times acceleration, and Fg minus Ft equals m times a. Fg would be 200 newtons minus Ft equals 20 kilograms times a. And then on the green side, the sum of the forces equals mass times acceleration. But the winner there is Ft minus Fg equals m times a. Ft minus 20 newtons equals a mass of 2 kilograms times a. Okay, so now we have two equations and two unknowns that we could solve for the acceleration and the tension force. So if I take the blue side, say, and let's solve it for Ft. So if we add Ft over and then subtract 20 kilograms times A over to the other side, we get Ft equals 200 newtons minus 20 kilograms times A. And then we can bring that and plug it in over here. 200 newtons minus 20 kilograms A. So we're plugging that in for Ft here. Minus 20 newtons equals 2 kilograms times A. Okay, so let's try to clean this up a bit. 200 minus 20 is 180 newtons. Add the 20 over. We get 22 kilograms times A. 20 kilograms A plus 2 kilograms A is 22 kilograms A. So A equals 180 newtons divided by 22 kilograms, which is 8.2, and as we've seen, that's meters per second squared. Now once you have the A, you could bring it in over here, plug it in, so Ft equals 200 newtons minus 20 kilograms times 8.2 meters per second squared. 200 newtons minus 163.6 newtons, and the tension in the string comes out to be 36.4 newtons. Okay, so that's just an example problem for an Atwood machine. 2 free body diagrams, 2 equations, 2 unknowns, solve them. Okay, part 5.3 is what's called chunky dynamics, or larger dynamic problems. So if you remember last unit, we did free body diagrams with like signs hanging, sitting on scales, or a pulley with a block on a ramp and a block hanging. And we were able to find unknowns that way. But in this case, instead of being in equilibrium, we'll have an acceleration. So the first example problem is the system below, which I haven't drawn yet. It's accelerating up the ramp to the right, and the angle of the ramp is 30 degrees, and mu is 0.2. So it looks like this. We got a ramp at 30 degrees, pulley on it, connected around to a block, to another block that's hanging off. And this is 40 kilograms, this block that's hanging. And this is 12 kilograms here. And mu is 0.2, and it says that it's accelerating up the ramp, so that's going to be important for telling us what direction friction is. So what is the tension in the cable? Okay, is the question. And what is the acceleration of the system? Okay, so we have to start with free body diagrams. So the block that's on the ramp, it has an FG down and an F perpendicular, like so. And it also has a tension force in the direction of the string. It also has some friction. Remember, it's accelerating up, so the friction goes down the ramp. And then the component of Fg in the plane, F parallel. The block that's hanging, a little simpler, it has an Fg and an Ft. So just like last unit, we do the same thing here. So except the sum of the forces is not equal to 0, it's equal to mass times acceleration. So for the one on the ramp, we have our sum of the forces is mass times acceleration. And our winner, the bigger, minus the two losers, FF and F parallel, equals mass times acceleration. So that's just for the ramp one. And now we can fill in some things that we might know for it, okay? So if we take friction, well, equation for friction is mu F perpendicular. And mu is, we are told, is 0.2. And F perpendicular will be Fg cosine theta. So Fg would be 120 newtons because it's a 12 kilogram mass. So here we would have 0.2 times 120 newtons times the cosine of 30 degrees. If we put that into a calculator, we get 20.8 newtons out for that. F parallel is Fg sine theta, so that would be 120 newtons sine of 30, and that would be 60 newtons, equals the mass of the block, which is 12 kilograms, times our acceleration. Now, minus 20.8 minus 60 is minus 80.8 newtons, equals 12 kilograms times A. We end up with that from the one from our sum of the forces equals mass times acceleration on the ramp. Now, the one that's hanging, we do the same thing, but now our winner is Fg and our loser is Ft. Those are the same Ft's though, equals mass times acceleration. Fg would be 400 newtons minus Ft equals 40 kilograms times A. And now we'll take, well, let's take this one right here and solve for Ft. So Ft would equal 12 kilograms times A plus 80.8 newtons. And then we'll bring that up here and plug in. So that would give us 400 newtons minus, sometimes it's good to put the parentheses in at this point because we don't want to forget to distribute the negative. Okay, equals 40 kilograms times A. So let's distribute our negative now, 400 newtons minus 12 kilograms times A minus 80.8 newtons equals 40 kilograms times A. 400 newtons minus 80.8 newtons is 319.2 newtons. And if you add the 12 kilograms over to the other side, or 12 kilograms A over to the other side to get that, and then A would be 319.2 divided by 52, which equals 6.14 meters per second squared. Now, taking that back over and plugging it in gives Ft equals 12 kilograms times 6.14 meters per second squared plus 80.8 newtons. So Ft equals 154.5 newtons. Good. All right. So that's an example of a larger dynamic problem. Here's another one. The hanging block below, which I haven't drawn yet, has a mass of 10 kilograms. At the instant shown, the hanging block is accelerating down 3 meters per second squared. The block on the ramp has a mass of 15 kilograms. What's the Ft and mu on the 20-degree ramp? So in this case, we have one sitting there like so, a block on a ramp connected around a pulley to another block below. And the hanging block has a mass of 10 kilograms. The ramp's at 20 degrees. The block on the ramp is 15 kilograms. A is 3 meters per second squared. And I think that's what we're given for that. And we want to come up with mu and the tension. Okay. Again, we start with free body diagrams for both. The one on the ramp would have Fg down and F perpendicular. It would have F parallel and a tension force. And friction would be working against it. Okay? And then the one hanging would have an Fg down and a tension force. And then we will do the sum of the forces for both systems here. The sum of the forces for the first one equals mass times acceleration. And we have the two larger winners are Ft plus F parallel. And those are winning out over friction in the first one equals mass times acceleration. So let's see what we were given here to solve for this. Well, we were given Ft we don't know, but F parallel would be 15 newtons times the sine of 20 degrees, and FF would be mu times 15 newtons cosine of 20 degrees equals a mass of 15 kilograms times 3 meters per second squared. 15 times sine 20 is 5.13 newtons. And we don't know what mu is, but we can get the rest. 15 cosine 20. That's 14.1, and the other one's 45 newtons over here. So let's continue to clean this up a bit. Well, we'll solve it all for FT here. First off, subtract 5.13 from 45, gives 39.87 newtons, and then add the mu, 14.1 newtons over, like that. Now the other diagram over here, the sum of the forces is mass times acceleration. The winner's Fg minus Ft equals a mass, which is 10 kilograms, times A, which is 3 meters per second squared. So Fg would be 100 newtons minus Ft, which will equal 30 newtons, which means that Ft equals 70 newtons. Now we can come and plug that back in to our other equation. We have the tension force, and we would have 70 newtons equals 39.87 newtons plus mu 14.1 newtons. 70 minus 39.87 is 30.13 newtons equals mu times 14.1 newtons. So mu equals 30.13 newtons over 14.1 newtons, or 2.14 is our mu. That's quite a sticky surface. Okay. And that will end that unit. Okay, I realized a mistake that I had made because I used 15 newtons. Maybe some of you realized during this, because it seemed like when I finished that the mu was way too high for this example. So I was wondering, I paused it and was wondering what it was, and went back through it to see where I may have made a mistake. And the mistake came in here where it's F parallel and FF, because I wrote 15 newtons, but it really should be 150. And this one should be 150 here. So 150 sine 20 is 51.3. And then this would be 141 newtons. Oops. Yay. So let's just erase it from here. And if we add the 51.3 over to the other side, we get 45 plus 51.3, which is 96.3 newtons. The good thing is I realized the mistake, but that's not always so easy. And then that gives 26.3 newtons. Well, hold on a second here. This is plus. Shouldn't get a negative mu. Okay, let's see. Subtract 51.3, subtract 51.3. Ft minus mu, 141 newtons. 45 minus 51.3 is minus 6.3 newtons put in the 70 newtons. Track 70 newtons. Ah, 0.54. So that makes sense. Okay. Well, sorry about the mistakes, but caught them. Okay.